Chapter 6, Number 77, A Classic in the Field. A hockey puck of mass M is attached to a string that passes through a hole in the center of a table as shown in the figure. The hockey puck moves in a circle of radius r. Tied to the other end of the string and hanging vertically beneath the table is a mass M. Assuming the tabletop is perfectly smooth, what speed must the hockey puck have if the mass M is to remain at rest? So let's do some highlights here. Most importantly, perfectly smooth, no friction. So if we think about our two objects, which I'm going to rename or rechristen a little bit, M1 is the guy going in a circle, and M2 is the guy block that's just hanging there. So we need to sort of sketch our thing. So I'm going to say from above, we're watching the puck, and it's going to go in some sort of circle, sort of around like that, where there is, of course, the hole right there. And at this moment, there's a string pointing towards the hole, and there's a velocity. And at that moment, the velocity looks like that, which means that there's a centripetal acceleration also towards the center of the circle. With magnitude AC. If we viewed instead from the side, then we would have the puck, which would look something like this, and there would be a tension pulling it that way, and of course there would be gravity pulling it down, and the normal pulling it up. I'm going to replace gravity with what we know it's equal to, which in this case is the force of gravity is m1g. And as said before, there is a acceleration towards the center, which at this moment looks like that. And then we have mass 2, who is way easier. There is just its own weight pulling it down, and the tension holding it up. All right, then we just do free body diagrams. So we say on block 1 in the x direction, there's just the tension, and since I happen to draw it this way, it has a minus sign because we usually take rightward as positive. And then vertically on box 1, there is a normal force minus the weight, and on block 2, which is only in the y direction, there is a tension minus the weight of box 2. And all of these things are from the free body diagram. From Newton's second law, we have a similar kind of thing, where we'd have F1x, F1y, and F2y, and each of these would be the appropriate mass times the appropriate acceleration. So in the horizontal, we have minus AC. And in the vertical, we'd have 0. And here in the vertical, we'd have 0. Because the block is hanging, we assume, outside, not even to assume, we are given the block hangs at rest. So it's not accelerating either. All right. And then what we should do is just combine these, which I'm going to go to a different screen to do. But we can just take these two sets of equations and make equivalences like this equals that, and so on. So our equations become minus ft is m1 times minus AC, and then also Fn minus m1g is 0, and then Ft minus m2g is also 0. And now we can use that this ft is that ft. Along the way, I think we'll start with the additional statement here, just quickly, that ft has to equal mac. So we have putting this one and this one together. We have mac, that m is m1, minus m2g equals 0. Or m1 v squared over r minus m2g equals 0. Or m1 v squared over r equals m2g. And we can solve that as saying v squared equals m2gr over m1, or the seed v has to be the square root of m2gr all over m1. Or in terms of the way they wrote their problem, just going back to the symbols that Walker had, we have a hanging mass capital M times gr over lowercase m, all square rooted.